it absorbs energy. Okay?
Yeah.
But it is not so when you, for phosphorus, actually it is 6.75 kilojoule per mole, not even 6. Whereas phosphorus plus electron, it gives you minus 72 kilojoule per mole. Nitrogen, phosphorus, they are in the same group. They are having the identical electronic configuration S2P3. But nitrogen absorbs electron energy, phosphorus releases energy. So, beryllium, helium, when you absorb energy, when you add electron, it absorbs energy 48.3 kilojoules per mole. Neon, 115.8 kilojoules per mole. Argon, 96.5 kilojoule per mole. Xenon, 77.2 kilojoule per mole. Does it release energy? It absorbs energy.
Yes.
If it is negative, the energy is released. If it is positive, the energy is absorbed. So is your definition correct? I showed it.
Yes.
But if you look at the book, they always write this. So electron affinity is a very tricky parameter. What we can say, I tried to analyze the electron affinity and I found very difficult to make a generalization. But one thing I could make is the electron affinity of second period except group 1. Again, there is an exception. Second period is greater than, the second period is less than third period.
Yes.
Okay? Let me give you some values so that you get convinced. Boron, minus 26.7 kilojoule per mole. Boron is a second period. Look at your periodic chart. Periodic chart. Open your periodic chart and see. Boron, second period or not?
Yes. Yeah.
Second period?
Yes.
What is the third period element of boron subgroup?
Aluminium.
And aluminium gives me minus 42.5. So third period is greater than the second period?
Yeah.
Carbon,
Gallium.
minus 121.9.
Yes.
Silicon, minus 133.6. That is valid? Third period is greater than the second period? Okay?
Yes.
Nitrogen is less than phosphorus. I have given you the values.
Yeah.
Oxygen is minus 140, say minus 141. What is the third period of oxygen subgroup? Sulfur, minus 200.4. Fluorine, minus 328. Fluorine, minus 349. Okay? Different groups, we have different. 13th and the 14th subgroup, electron affinities are different. But one thing is common, that the second period is less than the third period. except group 1, where lithium is greater than sodium. Otherwise, the third period element will be always greater than the second period, irrespective of the group.
Yes.
You have seen that the helium 48.3, neon 115.8. So third period is greater than second period, but the fourth period is not greater than the third period.
Third. Yes.
Okay? Fourth period is less than the third period. So what is common, except group 1, is the third period element will have a higher electron affinity than the second period element. Second, this first electron affinity could be exothermic, as in majority cases it is exothermic. But there are cases where it is not exothermic, where you have the half-filled or full-filled configuration.
Yes.
Here it is endothermic and not exothermic for the second period. For the third period, yes, phosphorus is exothermic, nitrogen is endothermic. Both have half-filled configuration. Both have S2P3. Nitrogen S2P3, 2S2 2P3, phosphorus 3S2 3P3.
Is to repeat.
And nitrogen, I told you, N to N minus 6.75 kilojoule per mole. And phosphorus plus electron to give P minus is 70,
2 minus.
2 kilojoule per minus 72 kilojoule per. That means the energy is reduced. So even here you see the difference. Both have half-filled configuration, but one is behaving differently from the other one. The heavier one is behaving differently from the lighter one. But we can see the third period is greater than the second. This much you can say except helium, alkali metal. Nothing more you can say about electron affinity. No generalization can be made. Second thing can be said that the second electron affinity.
Excuse me, sir. Sir, what is the reason that like nitrogen absorbs the energy and phosphorus releases energy when electron is added?
Site is large. Electron repulsion is less. You are having an extra electron. Since you are having an extra electron, if the size of the atom is small, the electron repulsion becomes more prominent. As soon as the size is large, it can accommodate the electron better.
Yes.
So it becomes exothermic.
Okay, sir.
Second electron affinity is always endothermic. Here also you see the difference. O minus plus electron gives O2 minus. 744 kilojoule per mole of energy is absorbed. Because now the electron repulsion is more dominating than the electron nucleus attraction. The energy was released due to electron nucleus attraction. Energy, when it's absorbed, the electron repulsion becomes more dominating than the electron nucleus attraction.
Yes.
Sulfide plus electron to give sulfide ion. The energy required. You see the larger size of sulfur atom can accommodate the extra electron better.
Yes.
So it is less endothermic than the lighter elements.
Yeah.
Oxygen is smaller in size than sulfur. So the larger the size, you can accommodate the extra electron better. As a result, it becomes less endothermic. So both are endothermic. Both are endothermic. But third period is less endothermic than the second period. Now, if the electron affinity is high, if an element with a high electron affinity will show oxidizing behavior. Element with high electron affinity will behave as an oxidizing agent. What is oxidizing agent? Which accepts electron? So what is the electron affinity? Which is the accepting of electron? So one is the reverse, it's the same thing. So element with a higher electron affinity will behave as a strong oxidizing agent. If you want to see this, what I said that why it is tricky, okay? You see terrible behavior. You can't generalize. Boron is less than aluminum, we can understand. That aluminum is greater than boron. But gallium and indium, they are equal, and thallium is the lowest. Okay? Okay, thallium is the lowest, we can understand because the distance from the nucleus and the outermost electron is the farthest. So the electrostatic attraction is the weakest. Okay. But in this case, you see, antimony is the second largest. Is greater than bismuth. Bismuth is greater than arsenic. Arsenic is greater than phosphorus. Phosphorus is greater than nitrogen. Phosphorus is greater than nitrogen. That fits me very well. So what you can see that silicon is greater than carbon, aluminum is greater than boron, sulfur is greater than oxygen.
Yes.
And
Yes.
chlorine is greater than fluorine. Can you make any other generalization? Different groups show different behavior. So how tricky is the parameter? It is not very easy to generalize electron atoms. Let me start with, you know electrovalent bond, covalent bond and coordinate bond, isn't it?
Yes.
Electrovalent bond, the bond results due to charge separation.
Charge separation.
That means the cation should be highly electropositive. Highly electropositive is related to low ionization energy.
Yes.
And the anion should be highly electronegative so that it can accept the charge very easily. That will lead to formation of ionic compound or ionic bond. Now it's called the electrovalent bond. What is the main difference between electrovalent bond and a covalent bond? You will answer that one results the separation of charge, another results the sharing of electrons. I'm not interested in that. Tell me something which is unique in electrovalent bond and unique in covalent. besides transfer of electron, besides sharing of electron. What is the difference? The electrovalent bonds are directionless. It's a non-directional. Whereas covalent bonds have directional properties. Okay? This is very, very important. Covalent bonds are in general formed by the hybrid orbitals.
Yes.
Isn't it?
Yes.
Why I said in general? Can you tell me why in general? Why covalent bond is not formed by the hybrid orbital? If a bond has to be formed by hybrid orbitals, it will require more than one electron. And hydrogen, when it forms a molecule, it is 1s1, 1s1 overlaps. There is no hybridization. So except hydrogen molecule, every molecule will have the covalent bonds are formed by the hybrid orbital, containing one unpaired electron. Methane. There is carbon 2s2, 2p2. But methane forms 4 CH bonds.
Yes.
So what I will do, we shift the s electron to p. And then we hybridize to form sp3.
Yes.
And the hybrid orbitals have directional property.
Yes.
So covalent bonds gets the directional property. So one is the reflection of the other, or one is a result of the another. Covalent bonds are formed by the hybrid orbitals, and the hybrid orbitals have directional property. So the covalent bonds have directional property. So it's a deductive logic, okay? That A is going to B or B is going to C, so A has to be equal to C. That is what I'm saying. Now, another is, difference is that the covalent bonds, there are two types of bonds. One is a sigma bond, another is a pi bond. Sigma bonds are always formed by the hybrid orbital, but the pi bonds are formed by the atomic orbital. So the hybrid orbitals include sigma bond and the lone pair, like ammonia. There are 3 NH bonds and a lone pair.
Yes.
So 3 sigma bonds and a lone pair are involved in the hybrid orbital, hybridization. So the number of hybrid orbitals will be 4, so it is sp. So the number of sigma bonds plus the number of lone pairs is equal to the total number of hybrid orbitals.
Yes.
In water, there are 2 sigma bonds, but there are 3 lone pairs. So the number of hybrid orbitals will be 4. So oxygen in the water is sp3. Now, what is the difference between a coordinate bond and a covalent bond? Covalent bonds generally
Equal
they
share.
form molecular like covalent compounds. Normally form molecular lattice. They are insoluble in water. And But the reaction rate vary. You can't predict that if it is a covalent compound, the reaction rate of reaction will be slow or fast. Some are slow, some are very fast. For example, carbon tetrachloride plus water. No reaction takes place. But silicon tetrachloride plus water immediately hydrolyzes to give you silica plus HCl. Both are covalent compounds, but their reaction with water differ. One does not react at all, another reacts very, very fast. Similarly, nitrogen trifluoride reacts slowly, whereas NCl3 reacts fast. Why they differ? Because in NF3, both are second period elements. So they cannot expand their covalency more than 4. There is no d orbital available to accommodate the incoming water molecule to undergo hydrolysis. Whereas in silicon tetrachloride, the silicon has a vacant 3d orbital which can accommodate the water molecule, expand its covalency from 4 to 5 and initiate the hydrolysis.
Yes.
Same thing is NCl3. Nitrogen doesn't have a d orbital, but chlorine has a d orbital. So the chloride ion can accommodate the water molecule, which in turn will assist the hydrolysis of NCl3. So NCl3 will hydrolyze readily, not NF3, because NF bond strength is very high. They are both of the second period. Their overlap is very strong. So the bond strength is very high. And there is no lone pair, there is no vacant d orbital available to accommodate the incoming water molecule. Whereas in NCl3, nitrogen doesn't have a vacant d orbital, but the chlorine has a vacant d orbital, which can accommodate the incoming water molecule to form the hydrolysis, to undergo hydrolysis, leading to the liberation of HCl. So, the covalent compounds, the reaction can help. The covalent compounds, if it exists as a discrete molecule, it will be either gas or liquid or a low melting solid, unless they exhibit a three-dimensional network with a polymer. A polymeric compound with a three-dimensional network or a polymeric compound with a two-dimensional polymer will give me high molecular weight, like quartz, diamond, graphite. They are not individual molecules. Coordinate bond is same as sigma bond. You can't distinguish a coordinate bond from a sigma bond. When the proton captures the electron from the nitrogen lone pair, this is a coordinate bond, but you
Yes.
can't distinguish which is a coordinate bond, which is a sigma bond, because all NH bond lengths are identical. But coordinate compounds, coordinate bond requires that the donor should have at least a pair of electrons and the acceptor should have a vacant orbital in order to form a coordinate bond. Because if the orbital is already occupied with at least one electron, no orbital can accommodate more than 2 electrons.
Yes.
Now since the donor gives 2 electrons to form a coordinate bond, So the acceptor orbital has to be completely big, so that it can accept a pair of electrons from the donor atom. Now, the solubility also it differs. Night covalent compounds, coordinate compounds also will show directional properties. They also use the hybrid orbital. Remember one thing, hybridization is a concept, is not a real process. Light resonance is a concept, not a real process. But tautomerism is a real process. You can isolate the tautomers, but you cannot isolate the resonating isotope. No. It is just our creation to help us understanding the science better. Without hybridization, I cannot explain why in methane all the bond angle will be identical, all the bond lengths will be identical. We cannot explain. That is why we take help of a hybridization process. But coordinate bonds could be, coordination compounds could be soluble in water as well as insoluble in water. Unlike covalent bond compounds, which we say is insoluble in water. And similar to covalent compounds, the coordinate compounds could react fast, could react slow. So you cannot, the rate of reaction of coordinate compounds will also vary. Now we go to transition elements. In JEE syllabus, the only first transition series elements are in today. And we have already, when I classified the elements, I have given you some idea about transition elements.
Yes.
The elements in which penultimate d orbital is being filled, they are called transition elements. And it starts with scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and copper. Now, if you know 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now, in your question paper, they will give you the atomic number. How do you know the electronic configuration? So, atomic number minus 83.
Equals to number of assigned
Is D and S electrons. Atomic number Z is equal to 24 and 29. It will be Dn minus 1 S1.
Yes.
And all other cases,
Yes.
it will be
Dn
Dn minus 2 S2. 2 electron in the S and the remaining in the D. Except for 24 and 29, where you have the S1 and the rest are in the D. So you know, as soon as you know the atomic number, you can predict what will be the outermost electronic configuration. Now, if we look at the transition elements vis-a-vis non-transition elements, you will see that transition elements show variable oxidation states.
Yes, sir.
Scandium shows +3. It has D1S2. Titanium shows +4 and +3. It has D2S2. And +4 is the one I underline. That oxidation state is the more stable oxidation. So you see, electronic configuration does not match the stability of an oxidation state. Have you finished?
Yes.
Okay. What I said, they don't try to equate the electronic configuration with the stability of an oxidation state. And that you can see for chromium and copper, it is vanadium, it is quite visible. Iron, it is quite visible. Cobalt, it is quite visible. Nickel, quite visible. Copper should have been +1 because of the fulfilled configuration, D10, but it is plus. Chromium should have been +1 for half-filled configuration, but it is plus. Vanadium should have been 5+, but is +4. Titanium, it matches 4, 4, 3, 3. So in some cases it accidentally matches, in some cases it does not match. I told you earlier probably, that hydrogen energy minus ionization plus sublimation energy, when it reaches maximum value, that oxidation state becomes most stable. This condition is to be satisfied to explain the most stable oxidation state. For all metals, whether it's a representative metal, whether it's a transition metal, or inner transition metal, for all types of metal, this equation will hold good. This condition will hold good. Now, one thing you can see, that as you go from left to the right, the tendency to show variable oxidation state increases. It increases and it reaches maximum when you reach manganese. Isn't it? Manganese shows the maximum number of positive oxidation state. Thereafter, so the tendency to show variable oxidation state increases from scandium to manganese, and thereafter it decreases and it goes to zinc. So when it reaches manganese, you have enough number of d electrons, 5 d electrons, and by that time the imperfect shielding by the f electron has resulted in increase in effective nuclear charge. Beyond manganese, it does not allow all the electrons to be ionized. As a result, the highest positive oxidation state is becoming low and low. So you see here +7, it is +6, it is +4, it is +4, it is +3, it is +4. So initially it allows all the electrons to ionize, giving rise to maximum positive oxidation state. Beyond manganese, the effective nuclear charge now dominates and does not allow all the electrons to be ionized. and as a result, they show a lower oxidation state. The number of oxidation state decreases, and when you read zinc, it shows only one. Okay. But there are compounds where the metal shows oxidation state 0 or even negative. Especially when it combines with carbon monoxide to form metal carbonate. So when metal combines with carbon monoxide, it shows 0, -1, even -2 oxidation states. Now I've written down some formulas. All are not correct, okay? But you can see carbon monoxide is a neutral ligand. There is no charge on carbon monoxide. So what is the oxidation state of nickel?
0.
Everywhere 0?
0. Yes.
What is the oxidation state of iron?
Minus 2.
-1,
Minus 1.
But not all of them exist, okay? How do I know which will exist, which will not exist? So, there are two rules. One is a effective atomic number rule. Effective atomic number rule. This states that count total number of electrons of the metal plus 2 into number of carbon monoxide, and if sum total becomes 36, then it will be stable, will exist. If there is a negative charge, you have to add 1 more electron. If there are 2 negative charges, you have to add 2 more electrons. Okay? Yeah. Now, tell me which one will exist, which one will not exist. For you, I will do the first two I will do. Nickel, atomic number 28. That means 28 electrons are there because atoms are neutral. And plus number of carbon monoxide is 4. 4 into 2, that is 36. So it will exist.
Yes.
Iron, what is that number?
26.
26 plus 5 into
10.
10.
Exists.
It will exist. This one?
Exists.
This one?
25.
No.
No, does not exist.
Does not exist.
This?
No. Wait.
Yes.
No.
23 plus 12, 35.
Yeah.
Okay. Then this one? Will it exist?
Yes. Yes.
Yes, sir. Yes, sir.
26 plus 8, 34 plus 2.
Plus 2, 36.
36.
So it will exist? Will it exist?
No.
This?
Exist.
25 plus 10 plus 1.
1. Yes. Exist. Yes.
Will it exist?
Exist. Yes.
27 plus 8 plus 1.
36.
Yes.
So, this will exist. So, this will not exist, this will not exist, this will not exist. But, I have put an ellipse type of thing.
Exception.
It exists as an exception. But if we look at the structure of carbon monoxide molecule, do you see anything unusual in this structure?
Yes. Yes.
Do you see anything unusual?
Yes.
What is the unusual?
So that carbon is less electronegative than it is taking, but although it is less electronegative, it is attracting the electrons there.
Oxygen is more electronegative and is still giving electrons. Why? Because what is the other alternative you have? That is the other alternative structure you have.
Yes, sir.
Now in this case, the oxygen attends the octet.
Yes.
Each bond is a 2 electron. So 2 bonds, 4 electrons plus 4 electrons. It attends octet. But what about carbon? It has 6 electrons surrounding it. It has not reached octet. Since it is short of octet, so carbon in carbon monoxide becomes highly electronegative. So it attracts the electron from more electronegative atom to satisfy its octet. Now you see, the oxygen satisfies the octet. 2, 4, 6 and 2, 8. Oxygen satisfies the octet.
Yes.
Carbon 2, 4, 6 plus 2. Carbon is also satisfying the octet. Now what is the proof I have? That there is a back bonding from carbon to oxygen to carbon. In absence of back bonding, if it would have been this, there would have been large amount of dipole moments.
Yes.
But the dipole moment of carbon monoxide is almost 0. That means whatever negative charge has it acquired due to higher electronegativity, it has lost during the coordination. So while giving the electron, it lost the electron density, and so the carbon monoxide dipole moment is only 0.12 dBAR. It's close to 0. Do you expect that dipole moment to be close to 0 when oxygen is 3.5 and carbon is 2.5? 1 unit of electronegativity difference should give me a high polarity, but the dipole moment of carbon monoxide is almost 0. That indicates that the oxygen has given back electrons to carbon to satisfy its octet. Okay. Now, but when carbon monoxide is attaching to metal, it forms a coordinate bond to the metal. The carbon, the lone pair on the carbon is donating to the metal to form a coordinate bond. And the carbon monoxide accepts the electron from the metal to carbon monoxide. Now, carbon monoxide and nitrogen, what is the similarity? Or what are the similarities?
Isolate.
2 molecules and 14 electrons.
Isoelectric.
Isoelectric.
Isoelectronic, not isoelectric. They are isoelectronic. And what else? Both are diatomic molecules.
Yes.
Yes.
So both are diatomic, both are isoelectronic. Okay. You have done molecular orbital theory?
Yes, sir.
So 1s sigma is less than 1s sigma star. 2s sigma is less than 2s sigma star. 2p pi is less than 2p sigma. And 2p pi star is less than 2p sigma star. This is the energy level up to nitrogen.
Yes.
Now, how many electrons we have for carbon monoxide? 6 plus 8, 14 electrons.
Yes.
2, 4, 6, 8, 12, 14.
Yes.
So in this is a bonding orbital. This is anti-bonding orbital. Star means anti-bonding. So it cancels. Bonding, anti-bonding cancel. You have 4 plus 2, 6 bonding electrons. By 2 is the bond order 3.
Yes.
Anti-bonding, there is no electron.
Yes.
Now, if the metal gives the electron to carbon monoxide, where will it enter? It has to enter into the vacant orbital, which has the lowest energy vacant orbital, lowest unoccupied molecular orbital. That is called LUMO. Lowest unoccupied molecular orbital. Which is your lowest unoccupied molecular orbital?
2p pi star.
So if the electron enters into the antibonding orbital, what will happen with the bond order?
Bond order will decrease.
Stability is also decreased.
So,
Stability also.
2 years back, they have asked this question, that CO bond order Can you predict the CO bond order? 1, 2, 3, 4.
3, 2.5,
3, 1, 2, 4. 3, 1, 2, 4.
From the,
3,
you said 3,
1.
bond order, 3 is greater than,
1.
1 is greater than,
2.
weak.
More negative charge in the metal ion. More electron rich is the metal ion. If the metal ion is having more electron, it will be a better donor of electrons.
Yes.
So, since metal is too negative in the 4, so it is the most efficient donor of electron. And since the electron is entering into the antibonding orbital, so CO bond order decreases. So the lowest CO bond order will be 4. Then this one, you have written correctly. Then 3, because the metal is positive,
Yes.
electron deficient, so it will not be a good donor. So the CO bond order will be high. And M's metal is 0, is better electron donor than M plus, because metal has more electron than M plus. While metal is 0 oxidation state, it is less electron deficient than metal is plus 1 oxidation state.
Yes.
So metal will be a better electron donor when it is 0 rather than when it is plus 1.
Plus 1.
Better the donor, weaker is the CO bond order. So this is the order. Is it clear?
Yes.
Sir, please explain that third one. How did it
Explain how.
Sir, how is third greater than first?
How is third greater than first? Because of the positive charge on the metal ion, the metal is a poorer donor of electrons than one where metal is 0. Now, if metal is a poorer donor, it is giving less electron to antibonding orbital. So the CO bond strength is high. So 3 will be the CO bond strength in 3 will be the highest because it has a positive charge on the metal ion. Because of the positive charge on the metal ion, the metal becomes electron deficient, so it will be a poorer donor. Then metal, when it is 0 oxidation state, where metal is less electron deficient, so it's a better donor, and so the CO bond, the electron enters more into antibonding orbital, so CO bond order decreases.